Hello everyone, welcome to Module 9 on latent variable models and the expectation maximization algorithm. I'm actually really excited about this one because EM algorithm keeps on coming up over and over again in different machine learning contexts. It's a very interesting topic, and let's begin. So the big picture is this. Many machine learning problems can involve some hidden structure behind the scenes that we don't directly observe in our data. Like there's some kind of variable that is producing the data that we're actually measuring in our environment, but we don't have access directly to that hidden variable. So hidden structure, latent structure, those are synonyms for our purposes at the moment. So some examples of this hidden structure can be, we have raw weather measurements. So we have like air pressure, we have wind and direction, we have temperature, precipitation. We have a lot of like raw measures of the weather, but we don't necessarily have like a direct measure of the climate variable that is kind of responsible for all of these observations we're obtaining. And what we really want is like some kind of abstract core model of climate. We may be running a store. We have lots of purchase receipts. We have a lot of data in our data warehouse that describes buying behavior and the various products that we're selling. But what we really want is an understanding of like who our customers are, who our users are. Are there different groups? Do they respond better or worse to different products, different sales? We want to better understand like our users at a high level, right? So what are their behaviors? What are their personalities? I can't see that on the receipt, but their behavior, their personality is kind of in some sense generating what I can observe on the receipt, right? Like people who want to spend more will buy more expensive things, as a crude example. Similarly, even the text you see on the screen right now, you can see the individual words and characters, but hidden kind of beneath the surface are the topics that this text is about, the intentions I have in informing you about these topics. Both of those hidden variables, my intentions, the topics behind the scenes, in some sense has a statistical relationship with all these words you see on the screen right now. But you can't actually measure, in my mind, like what my intention variable is, for example, but you'd kind of maybe like to. So latent variable models, as the name might suggest, lets us write down this probabilistic story using hidden variables that we can guess are there. And we'll use something called the expectation maximization algorithm, or the EM algorithm for short. This will give us a practical way to fit these models, essentially using maximum likelihood estimation like we saw earlier. What we'd really like maximum likelihood has all these great properties which we saw in previous modules. We'd really love to do maximum likelihood estimation. The problem is that there's some hidden variable we don't have access to, so we just can't do the counts. We can't iterate over possible values of that hidden variable because we don't actually have access to that variable. So we have to do some guessing, and using our best guesses, we can basically run a modified form of MLE. So that's the high level idea. So just to recap from Module 8, fully observable maximum likelihood estimation. We have our data set, which consists of data points, x sub I, and there are n of them. And there's a model family, described probabilistically as the P of x, and it has parameters theta. So we described likelihood before. Likelihood, big L, is in some sense a measure of theta. It depends on the data set we have, so it's written in this kind of form, but essentially this boils down to the probability of the data set itself using the parameters theta. And we've previously defined this as just a product over all of the individual probabilities of the individual data points. There's some assumptions built in here that we can skip over for now. Like it's possible in some circumstances that the observation at time t might depend strongly on the observation at time t minus 1, but for now we're assuming these things are all independent and identically distributed. Okay? So the overall probability of a data set is just a product of the individual probabilities of the data points. The log likelihood, we talked a lot about like why we'd like to do things in the log space. So you take the log of a product, that gives you a sum of logs, which is how we get to this line down here. And then the maximum likelihood estimate, like the parameters that we prefer, are the parameters that maximize the log likelihood, okay, using the data kind of hidden here. Okay, we talked at length about this in Module 8. If it's unfamiliar, go back and revisit Module 8. There are some simple models, like the Bernoulli model, like flipping coins essentially, or the Gaussian distribution, where we had closed form MLEs. What that means is if you wanted to get the optimum parameter for a Gaussian, and you have all the observations X at your disposal, then there's a simple formula for computing mu. It's just the average of all of the observations you have. We derived that, but the end result is something simple and closed form. We also had access to and could measure all of the necessary variables. So we kind of always assumed that all of the variables we needed were right in front of us. But now we're aware that there's something behind the scenes. We're not going to have access to it, but we're going to infer or guess at it. Okay? So this is key. What is beneath the surface? Some part of the data is missing, unobserved, or latent. In reality, this is almost always the case. Like there's no situation where you're going to have a complete, unfettered view of the universe. So we always have a situation where we have latent variables. It's just a matter of how detailed we want to be in modeling them. So our example today is going to be vibration monitoring. So we're part of critical infrastructure. We have a wind turbine. There's lots of these around the Atlantic Canada. It's very important for clean energy. And but we want to ensure that all of these turbines are operating effectively. So every minute we record a sort of vibration amplitude, which we measure X in millimeters per second, right? How much these things are vibrating. Right? We don't want them to vibrate too much. Okay? The more they vibrate, the more they're at risk of failure. So there might be two modes behind the scenes. One mode is normal, everything's fine. There's a healthy blade, everything's spinning normally. Another mode is high wear. So this is an old blade, it needs to be replaced. It's at high risk of failure at any moment. We need to attend to it. Okay? I'll return to this later on in this lecture. This looks very much like a classification problem. We have a measurement X, and we want to infer something about some other variable, in this case, the operating mode. We'll come back to that later on in this module. I can see the connection, and to some extent that's what we're going to be doing here. But in normal situation, when we're dealing with latent variables, we don't have labeled hidden states. I'm making these labeled here just for the sake of explanation, just so you can follow along in this module. But normally we have no idea if there's 2 operating modes, or 3 or 4 or 11, and so on. We have to guess at that. So right now we're guessing there's 2 possible modes, and we have labels for them. We understand what they are, but hopefully you can understand that in practice and in general, we don't know how many, we understand that as a variable. We can call it operating mode, but we don't know how many possible modes exist, and we certainly don't know labels for these different possible modes. It is something obscure and hidden from us. But carrying on with this sort of assumption for now, we're certainly not going to observe the mode directly. Okay, we're not going to have a special column Y with labels normal, high wear, normal, and so on. We never observe these. We only observe X. And the context here is, well, we have stakeholders like we often do. In this case, they're reliability engineers. We have decisions to make from our data science process, which time windows and which turbines flag for inspection. When we send people out to inspect turbines, there's costs, right? So there's costs of a false negative. If a wind turbine is about to fail and we ignore it, that's a false negative. We miss situations where there's high wear, and therefore one of these turbines fail, there's unplanned outage, there might be damage that's unrepairable, there's cost associated with false negatives. And again, there's also risks or costs associated with false positives. So if there's a turbine where everything's fine and we flag it as possibly high wear, we'll send somebody out to inspect it. We have to pay them for their time, we have to pay them for their fuel to get to the turbine in the first case. This is wasted time, wasted effort, which could have been used elsewhere, so there's costs associated with false positives also. So we want a probabilistic model that basically will tell us what is the probability of seeing this observation, this vibration amplitude, given that we're in one of these modes for each of our possible modes. Right? So we don't know what mode we're in. We observe something. What is the probability that I'm observing this if it's normal? What is the probability that I'm observing this if it's about to fail? And we want probabilities for those cases. To do this, we'll have to guess at or infer the posterior probability of each mode at each time. Okay, and fortunately, we'll be able to fit this probability distribution just from the vibration data alone. So even though we don't have any access to mode, we'll be able to still fit a probability distribution using EM. So this is a classic case for something called a Gaussian mixture model or expectation maximization. So expectation maximization shows up in all kinds of contexts, but one of the easiest to visualize is Gaussian. So we're gonna dig in on that now. So here's our general story. We have observed variables x. These are the data we actually see. We have latent variables z, which are the hidden variables that we assume exist. So these are, we call them like topics before, states, modes, clusters, the previous examples. Like depending on the context, you're going to have different guesses at what the latent z sort of means. Because we have these two variables now, because we have variables x, which we observe, and z, which we don't observe, we have to have a joint model of them. We have to understand how these two relate to one another. So we have this joint model probability of x and z together. And because we can apply the chain rule, we can rewrite the left-hand side as the probability of z by itself times the probability of x given z, which is what we mentioned a moment ago we want. We want this conditional here on the right. Okay, we're going to have to also guess at the prior probability of z by itself, but we'll get there. Okay. Given all of this, we can get the observed data likelihood by summing out z. Actually, you can do this directly from just this joint probability. So we'll come back to this joint model in a moment, but we can go back and we can just say, well, the probability of x by itself will just sum over all possible values of z, and this will give us the probability of x, which is what we see over here. Okay, so for all the possible values of z, we compute the probability of x and z. This will give us the total probability of x over all of those possible pre-existing conditions or hidden states. So we still have our data set, which is just of observed data x. We still have n data points. We still want to take the likelihood. We still want to take the log likelihood. So the log likelihood is just going to be the log of the probability of our data set. But because the data set now looks like this, it's a bit more complicated. So the log, again, every data point will still be represented by a probability, the probability of a data point here, down here at the bottom. Can I do that? There you go. Unfortunately, this is a sum. So it's going to be a product over all possible x's, and every term, every factor in that product is going to be a sum that looks like this. So a log of a product is going to be a sum of logs. So we have a sum over all of our n. We get our log, but now we're starting to run into some problems. We have another sum now, a sum over all of our z's, our hidden variables, and our complete joint probability, which we can rewrite in these two factors here. Okay, this is getting a bit hard to optimize already, but we can do it. So here's kind of like the default gateway model that we use for learning expectation maximization. So x is going to be one-dimensional. It's going to be a real valued number. This is our vibration amplitude from our turbine example. And z will be our discrete mode. Okay, so I mentioned earlier, well, I started saying, well, maybe this is normal mode or it's like an at-risk mode, but I also mentioned that we don't necessarily know how many hidden modes there are, right? So it could be 1, it could be 2. In general, it will be k. Okay, so it's important, like we have k possible discrete hidden modes. We're going to redefine a couple of things. Okay, so I previously had the probability of z. I'll go back just for argument's sake. This factor over here, right there, probability of z by itself. So another way of writing that is just like the probability that the variable z takes a particular value. The particular hidden mode we're in now is mode k. And I'm just going to rewrite this just for convenience as omega sub k over here. So this is the prior probability, like ignoring the actual data. What is the prior probability or the initial probability that it happened to be in a particular state k? Okay, that's all it's saying, right? Because this is a probability, if I sum over all of my possible values of k, all of my possible hidden states from 1 to big K, because it's a probability, the sum will be 1. Okay? And now we have our conditional. So the conditional is a probability of x given a particular value of z. That is, I wrote over here as this factor. I'm going to assume things are Gaussian now. So we're assuming we're using a normal distribution, n. That's just going to be the probability of x. I should have rewritten this. This shouldn't be a given. This should be the semicolon. But I'm using mu sub k and the variance of k. Okay, so remember, a Gaussian has two parameters, its mean and its variance. Okay. So what parameters do I have in total? Like in my new model now, I have not one Gaussian, but I have k different Gaussians. Right? So if z is equal to 1, I'll have one particular Gaussian. If z is equal to 2, it's another mode, I'll have a second Gaussian. If z is equal to 3, that's third mode, I'll have yet another Gaussian. Each of these Gaussians will have different means, different variances. Right? So in total, what parameters do I have? I have the prior probability of being in a particular mode, which I call w sub k. In that mode, I have a particular mean value, mu sub k. And I also have a particular variance, sigma squared sub k. Okay? So all that is to say, I can rewrite or reframe the probability of x as a sum over the possible values of my latent variable. Before I called that a sum over z, possible values of z. Well, now z is my k discrete states, so I had a sum over all of my k states. I have the prior probability of being in that state times the posterior probability of the observation given the state. So this somewhat fancier looking equation down here is literally just this equation over here. Okay? Actually, sorry, it's this equation here, the sum over z, but I've rewritten p sub theta as these two factors. So that's the sum over z, here's the sum over k, here's a prior probability of value z, here is my prior probability, here's my posterior probability, and here's my posterior probability of x, using my state. So for a particular data, x sub I for all of my I, we still want to optimize these parameters. So we can still fiddle with the knobs until we have the best possible parameters that maximize the overall probability. Again, to get the best model, just like with MLE, we have a likelihood that is as big as possible. Right? So we want to maximize the log likelihood, just like we did before. Okay? The log likelihood is now going to be expressed in terms of this new sum and all these extra components. So here's the log likelihood. Here's the log of the product of probabilities rewritten as a sum of logs of probabilities. Now, here's where we kind of hit up against a wall. There's no closed form MLE solution for this because the latent variable z, which here is these k hidden states, is actually a quote hard optimization problem. But we can solve this, as you might expect, fairly easily. The idea is that, well, we have, this is loosely speaking, but we have observation x. Okay, so this entire sum over here, this inner sum, that is the probability of a observation x. Here it is over here again. Okay, this we can imagine that x, the data x, was produced by one of the individual hidden modes. Okay, so either x was produced or came from the first mode, k equals 1, or it was generated by the second mode, k equals 2, or the third or the fourth, and so on. Okay, this still matches up with our turbine example. So, this observation x, this particular value of millimeters measurement could have come from a normal mode, or it could have come from a at-risk mode. What is the probability of x? Well, it's a probability that it came from the normal mode plus the probability that it came from the at-risk mode. We add those together, that gives us the overall probability of x. Overall possible explanations of how the data was generated. Okay. Now it's not exactly like switching between these two modes, because I'm still not really sure which mode I'm even in, right? I have a certain probability of being in one mode or another, but I can't guarantee that this observation came from one mode or the other, so I'm going to have to blend these things together somehow. I want to hammer home the reason why this is not like a simple case, I guess. Here's the code, which I welcome you to download and check out. It's a bit longer than maybe is usual. A lot of this is just for visualization. So I create a data set, which is the histogram in blue here. So all these blue observations is like my real data, which comes from like a bimodal distribution. There's two distributions at play. I could have a single Gaussian that I want to fit to all this data like I did before with maximum likelihood estimation. That'll give me this orangish dotted curve over here. Now this is not great, right? Obviously the histogram doesn't follow one single nice smooth curve. There's two bumps to it. So the single Gaussian I don't like. But I can imagine now that, well, I'm generating this data from two components, right? One component is this one. Another component is this one. And what I would like is to combine, so sometimes data is generated from this orange component, sometimes it's generated from this green component. For a particular observation, X over here, not knowing whether it comes from component 1 or component 2, I can mix them together. I can kind of, add the probabilities of observing X in both of those conditions, and I can merge them together given a weighting, which tells me what is the prior probability of being in component 1 or component 2, and that'll give me this nice smooth purple curve, which I call a mixture because I'm mixing these components together. And as you can see, this mixture is way better, a way closer fit. The colors changed, I'm sorry for that, but now the orange curve here, this mixture, is way closer to reality than this single variable, single mode Gaussian. Okay, so things are getting better. I'm getting better modeling by assuming some hidden structure already. So this is just a summary of what we mentioned a moment ago, really. We keep on seeing this pattern. Hopefully this is going to be clear. So the probability of X in a situation where I have observed X and hidden variable Z is I'm going to have to sum over all possible values of Z. Okay, and that'll give me the probability of X, which is kind of what I care about. That's what this orange curve is telling us. What is the probability of seeing X? This probability distribution, this orange curve, is much more complicated. Well, much more. It's more complicated than our kind of default simple way of looking at the world. And we can take this probability of X and Z. We can split it apart using the chain rule, which is a standard rule in probability, and get these two factors here. And and then we can handle things carefully, right? So again, this conditional probability of X given Z is has to do with observations kind of coming from a certain distribution, a certain component, and probability of Z is just like the probability of that component in the first case. And again, in case it's not clear, we never see Z directly, but we're going to sum over all of its possible values. This is a side note, so feel free to ignore this for now, but I wanted to kind of mention this because I feel that the what we're doing now has deep corollaries in different sciences, in particular physics. So I'm not a physicist by any means, but I'm vaguely aware of the fact that we have large bodies of humans and furniture and other things, which we can describe their properties and how they relate to one another using classic Newtonian physics. But as you get deeper and deeper into atoms and then to subatomic particles, that can the quarks that make up subatomic particles like electrons and protons and neutrons and so on, we can't observe them. It's not like billiard balls moving around on a table anymore. We have to describe them sort of statistically, right? And you might have heard a lot about quantum level mechanics or quantum theory. Again, I'm not a physicist, and we're not going to. It's not even in the scope of this class, so we're not going to talk about it now. But vaguely, the modeling of reality has to do with having to fit sort of probability distributions over the possible states of these subatomic particles, and then those distributions sort of collapse sometimes, and then they help us describe more macro level or more higher level states of electrons, protons, atoms, molecules, and so on. Okay, so that's obviously a side note, but I wanted to kind of make the connection between the computer science and the math, which is what this course is about, which is awesome on its own right, but is connected to our deeper understanding of reality. generally. Okay, not that every science has to be physics, but I like to make the connection. So there's a paper here by Sethna. It's a book which you can get over here. This describes these microscopic configurations that we don't observe directly, and there's something called a partition function, which you can totally ignore this. The form of this function looks very similar to like something like a Fourier transform, which is outside the scope of this course also, but it's nice to see the same kind of forms of equations kind of crop up over and over again. Anyway, the idea is that there's these macroscopic quantities like average energy, but these kind of macroscopic high-level quantities come from averaging over hidden states, in this case S, right? The idea is very similar to what we're talking about with our turbines. We only see the outcome, but the math has to sum over everything that could have produced it so that we can kind of describe it, okay? There's other papers here too. So this McKay link over here, and this modern latent variable energy-based perspective on machine learning from Dawid and LeCun. You can click here and read more about it. It comes from a recent paper in the Journal of Statistical Mechanics. I also want to, this is still kind of a bit of a side note, but it's more of a preview for our own class now. We want to characterize, like later on we're going to talk about neural networks and transformer models. Transformer models have these components called attention. And attention is sort of a soft way to define an observation at a particular time in terms of observations, or rather representations at other points in time. So we're trying to figure out what is the best word to go in this particular slot amongst all this other text. We'll have representations for the other text. And what word is best in this slot will depend a little bit on the words around it to various degrees. That dependence will be expressed as something called attention. Attention is essentially, well, here's a formula that will come up in the future. Attention alpha over here basically is the amount of attention you have to spend when you're trying to figure out a word at slot I to all of the possible other representations, all the other words in your text for that particular example. So A alpha sub ij is just like a soft connection from time I to time j, so to speak, or word I to word j. And because we don't necessarily know what the reality is that produced this text in the first case, we're just developing in the future a neural network to represent that hidden state, that hidden attention, the hidden relationship between words. We have to infer this magic thing called attention, or this hidden thing called attention. The magic doesn't exist, so we have to sum over it. So this is sort of like an expected value over this hidden choice of which other position j we're attending to. A very, very similar form, almost identical actually, to the Gaussians that we're talking about now in expectation maximization, which we're getting to. So we don't have to say, well, the word at this particular moment I only depends on this other word. It kind of depends in varying degrees to all the other context around it, but in a way that we have to guess at, and with a weighting or degree that we also have to guess at, and that's alpha, which we call attention, which we'll get to later. So the unifying thing here is that these latent variable models, which is kind of the subject of this module, and physics and deep neural network attention, all basically say the same thing. We have some observation X, but there's some assumption of some hidden process behind the scenes that we wish we knew. We have a kind of a model about it, but in order to get our probabilities of X, we have to sum over all possible hidden states that produce this observation X. So previously we saw something called gradient descent with maximum likelihood estimation. So in principle, we would like to be able to differentiate the log likelihood like we saw before, and this run gradient descent, find a point where the gradient becomes 0, which is our kind of stable point, and then that particular setting for theta will give us the highest likelihood of the data, and then we're super happy. We got the best possible model we could have. Okay, this challenge is obviously, which I hinted at earlier. So the log of a sum over k of these two factors together, this combined term, this will lead to non-convex objectives. So previously we assumed that this loss surface was kind of had a nice bowl shape, right? Where like if we kept on heading to the direction of maximum change, we would eventually hit our optimum, over which there's no other better setting. But now, instead of like a bowl shape, a single mountain, we have all kinds of mountains and all kinds of peaks and valleys in the theta to probability space, the loss surface. So if we try climbing a hill, so to speak, we'll get to some maximum of that hill, but there might be other hills that we just can't necessarily see, because all we can see with gradient descent is to stretch the metaphor, the ground at our feet. Okay, so we've reached kind of a local optimum, an optimum for this mountain or this hill, but there might be huge other mountains which we just can't see in this kind of blind ascent up the mountain, given the mountain range we find ourselves in. Also, for mixtures like this, gradients can be kind of messy to derive by hand, which is not a problem really, especially if like you're relying on other people's derivations that have already been done, but still it bears mentioning. It can be unstable numerically. So when these components become very peaked and very tight, then we run into just practical issues of numerical instability, like the inability of our computers to actually like hold the variables at the precision necessary to be accurate or precise. So what we would like, because of these problems, is something that will essentially reuse our familiar complete data formulas. Like we want to keep on doing MLE, and we're going to try to. And we're going to still try to use probabilistic interpretations, but we're going to have to do a little bit of tweaking, okay? And this is where the expectation maximization algorithm comes in, of which I'm a big fan, as you can tell by these emojis. So this is kind of this will make sense maybe more in retrospect than it might now, but the idea of expectation maximization is sort of like an iterative game. So we're not going to be able to just take one climb up the mountain and do everything in one go. We're going to have to kind of iterate over and over again. So the iteration goes like this. First of all, we'll just guess at what the parameters theta are in the first case. This is our initial guess at theta at time 0. They can be random. There are smarter ways of guessing them, but we'll leave that for now. Then what we have to do is we have to kind of estimate what the hidden structure is. Okay, so given the data that we have and our initial best guess as what the parameters ought to be, then we can use those two things together to make our best guess of what the hidden structure is. We can guess at what the probability of omega is. We can guess at what the probability of x given a Gaussian is. Okay, we're using our best guess for the thetas to do that. Now, if we've and that kind of brings z to the surface. So we don't measure z still, but we can guess at what z is given all the other information we have. Okay, we're not going to make a choice. We're not going to use this to say, well, the z is definitely this. We're not going to say the turbines are definitely in this mode. We're not going to say that the mixture of Gaussians is definitely in component 1 or definitely in component 2. We're going to say, well, there's a probability of being in state 1 or 2 or 3 or 4, and that's good enough for us. That's all we need. Because given that, kind of modeling of what z is, that'll allow us to essentially do maximum likelihood estimation. This m step over here, that'll help us update our parameters, like we did with maximum likelihood estimation, and then we just continue. We have better parameters than we did initially now, and we'll start with those parameters. Then we'll go to the e step. E stands for estimation, or expectation, and interchangeable, it doesn't matter. And then we'll estimate the hidden state again. Given that estimate, we'll redo the maximum likelihood estimation. M stands for maximum or maximization. And we'll keep on going and going until some condition is met. Maybe things stop changing. Maybe our overall likelihood stops getting better. Maybe we've run this algorithm, this EM algorithm, through a million iterations of E, then M, then E, then M, and we want to stop because it's getting late or whatever. We can stop with some condition and we're done. So a little bit of detail here. Again, this is essentially everything boils down to these two alternating moves. The E step, which you can think of as inference, and the M step, which you can think of as re-estimation. So given the current parameters, theta sub t, okay, so we started off with theta at time 0. After one iteration of E and M, then we're at theta of 1. We've gone through one iteration. So we go through many iterations. So at some random point during this iteration, we're at time t, or iteration t. Okay, so we've gone through, I guess, t minus 1 iteration so far. Or we've gone through t iterations so far. So we want to guess at how likely each latent configuration is. For a Gaussian mixture model, we want to basically compute the responsibilities for generating the data. This is the key we wish we had. If we knew that this data point was generated by this particular component, then we'd be finished. If we had that information for all the data points, we could just take all the data that were generated by component 1. We could say, well, the average of all of these components is this. That gives us mu. The standard deviation is this. This gives us sigma. We can compare the total number of points generated by component 1, the total number generated by component 2, take that proportion. That gives us the weightings, omega, of component 1 and 2, and we're finished. We don't have to do anything else. Okay? But we do not have that. We do not say, well, this data point was definitely produced by component 1. Okay? We have to guess. So, what is the probability that a hidden state at time I? Time I can also maybe better describe it as data point I. So we have n data points. For data point I, what is the probability that the hidden state at data point I was specifically k, or in other words, that k produced this observation x. So this might look a bit more confusing or complicated than it really is. This is actually a very simple formula. So in other words, what this is saying is, what is the probability, given the observation x, what is the probability that the hidden state was k, right? So this is what this probability here is saying. Given my current parameters theta, after t iterations, what is the probability that the kth hidden state observed this observation given the observation? Okay. Again, for convenience, just like before with omega, we're going to rewrite this as gamma sub ik. We probably won't say this that often anymore, but this is a simple shorthand to represent this. Now, this might be kind of complicated, but it really isn't. Some of you might be aware of something called the softmax function. All I really want, how do I compute this? It's what is the probability of, hidden state k specifically? Well, that's the probability of k and x, which is this numerator over here, divided by all possible values of z and x, which is the numerator down here. Okay, so given that I'm summing over all possible hidden states, and this now I'm calling it j, this sum boils down to the probability of x. That's the denominator, the bottom part. The top part is what is the probability of observing x and having z, or k rather, produce it. Okay. Maybe the probability of x itself is pretty low, so I need to normalize, which is why this denominator is here. Regardless, hopefully you can see where this is coming from. You can picture like a big circle describing the probability of x, which is that circle, and the probability of x is made up of a bunch of subcomponents. There's a probability that component 1 produced it, plus the probability that component 2 produced it, plus the probability that component 3 produced it, and so on for all of your possible components. All of this is going to, normalize appropriately, and we get the overall probability of x. And this is the fraction of that probability that was sort of that k was responsible for. I've said the same thing in a couple of different ways, so hopefully this is going to be clear. But if it's not, we have time together in class where we can talk about it. So, again, to summarize what we're doing here, I would like to know what z is, because if I knew what z is, then I could do maximum likelihood estimation. I can't decide or choose specifically what the value of z is, but at the very least, I can estimate what the probability of the different possible values of z is, given the parameters I have so far. Okay, and because this is a Gaussian mixture, I have my prior probability of a component, which is omega, and then I have my posterior over here, which is my normal function, which we talked about earlier. Okay, I think you all should know this by now, or you should all have guessed it anyway. But what's going on here is like mu sub k brackets t just means this is the mean value of the kth Gaussian after t iterations of the EM algorithm. So if t was 0, this would be my first random guess as to what the mu should be for component k. Okay, but so that's my first guess. But I assume at this point that these parameters have gotten better and better through this process. We'll say why that actually is the case soon. The M step is now like treating these responsibilities as if they're sort of labels, but soft labels. I want to refit the parameters like if we had this weighted data. So for a Gaussian mixture model, a mixture of a bunch of Gaussians, I'm going to update each of the kth Gaussians and its weight, omega, basically one at a time. Okay, so it might make sense well, I'll start with this one. Okay, so this sum over here, like I would like to be able to count the total number of times that Gaussian k produced my data, but I don't know, which Gaussian produced my data. All I have is my probabilities, and I computed them a moment ago up here. This is the probability that, given a data point, it was produced by the kth Gaussian. Okay, so I can't count those Gaussians, but I can sum over all of the probabilities. Okay, if I was 100% sure of what these probabilities were, then I just, for every data point, I would basically sum a bunch of ones and zeros. 100% probability that it came from k, a 0% probability that it came from k, and so on. And that's the good old-fashioned count. But now I have a soft situation. I may have an 80% chance, a 20% chance that the ith observation came from k. I computed that a moment ago over here. And I just sum over all of that. This gives me kind of a soft estimate for the number of times that Gaussian k produced a data point. And now I want to compute or recompute my parameters for my individual Gaussian. So my Gaussians are going to be my mu's and my sigmas. I'm just going to mention the mu's for now. So what is the new value I should set mu to? What is the, at the t plus 1th, t plus first iteration, what is my new best estimate for what mu sub k should be? Well, previously I just had a simple form of the average of x, for my one Gaussian, right? So I just, for every value of x, I sum them together, I divide by my total number of observations, and that gives me my average, which is mu. That's the MLE case. And I can't exactly do that now. I don't have an actual count of the number of times my Gaussian produced data, but like I just did a moment ago, I have a soft estimate for the number of times that my Gaussian k produced data. Okay, so I can normalize by what I just computed. Now for every observation, x, I want to sort of sum up its value, but I want to weight it with the probability that it was produced by my Gaussian. Okay, so like it's possible that x was produced by other Gaussians, and I don't care about that for the moment. I'm just trying to sum up for my Gaussian k, my new version of mu, right? So I multiply x by gamma sub I k, which I computed a moment ago. This just weights it for my k, and then this gives me a form which is almost identical to the maximum likelihood estimate for mu. Okay, I'm not going to go into sigma squared, and you can infer from that this is not going to be a crucial thing to remember, but you can tell also that you can go back to the slides on maximum likelihood estimation. You can look at the format we had for computing sigma squared. It'll look remarkably like this, except it'll use actual counts n, which we don't have, which we had to estimate a moment ago. And it doesn't have this weight, the weight that the observation I was generated by the Gaussian I care about right now, Gaussian k. So I add that there too, but that's kind of the only difference. Actually, I've talked about this more than I intended to, so I'll just kind of wrap this up a little bit. This mu sub k of t plus 1 is the mean I computed a moment ago. This is a bit of a pitfall that some people take if they're computing all of this from scratch. When I'm computing sigma squared, my new best estimate for sigma squared at iteration t plus 1, do I use the mu that I just computed a moment ago within this particular iteration, or should I use the previous version of mu sub k that I had in the previous iteration, in which case I'd have mu sub k at iteration t, not t plus 1. Okay, that we'll leave for now. That is a detail that we don't care too much about, but it's common practice for at least one reason, that we'll use the value of mu, the new best version of mu that we just computed a moment ago, for this iteration. If somebody is not paying attention, so I mean, all of you wouldn't do this, but if you're trying to explain this to someone else, they might get confused at this point. Like this, we know what's going on now, so we know that sigma squared is its own variable, which is variance, and this is the variance of the kth Gaussian at the t plus first iteration of my EM algorithm, which is where this parenthesis comes from. But somebody who's half awake might look at this and say, well, I can multiply 2 by t, and I can distribute the 2. So this is sigma sub k to the power of 2t plus 2. And that's not what's going on here, okay? Even though it looks like, given the way the math formula looks like now, we know better. We know that this is sigma squared at the t plus first iteration. And finally, right, so I wanted to, I had those 3 parameters I mentioned a moment ago. Where are they? They must have been a long time ago, so I'm not going to go back through the whole deck anymore, but we had 3 parameters that fundamentally are part of our Gaussian mixture model. There's the mu's and sigma squareds of the individual Gaussians, and then there's the weights of the Gaussians, the prior probability that the Gaussian produced data in the first case without caring about the nature of the data at all. So we need to update that also, because it's one of our parameters. So the weight of the kth Gaussian at the t plus first iteration is just the estimated number of times that we generated data from this Gaussian k divided by the total number of observations we have in our data set. There's a very clean way. This is a nice little formula. Hopefully it's intuitive. There's a little way that you could derive this yourself if you don't want to just memorize it, or even just sort of guess at it using, it's fairly obvious form, but we're done. So we wanted the hidden state. We didn't have it. We could guess at its shape probabilistically during the inference or E step. And given that guess of the shape, we could rewrite our maximum likelihood estimation equations a little bit, our mu's and sigma squareds over here, and we needed an estimate for n. So we did that. We estimated our weight components, which we need for our Gaussian mixtures. And then we're done. We have our new best estimates for each of our 3 core parameters. And if we wanted to, we can go back to step 1. Now, t is t plus 1, and we iterate and iterate and iterate until convergence. So here's a little bit, again, a good old-fashioned microscope is here. So this is more for the people who want to take a bit of an advanced step. We're not going to prove any of this. It's more of just a flag. So the big idea here is we have this distribution, not p of something, but q sub I of zi, where z is the hidden state. So this is a distribution over latents for every data point. And there's something called Jensen's inequality, which is almost certainly going to come up again later in this course, but not this module. This can be used to build a lower bound on what the log likelihood should be. This is sometimes called ELBO, which is the evidence lower bound, which I don't like because there's other famous methods in machine learning that are also called ELBO, but we have no control over that, so it is what it is. So Jensen's inequality will tell us basically what the lower bound on the log likelihood ought to be, given this distribution. And we can frame expectation maximization as alternating between the E step, where we have a fixed parameter, like we know we have. We have the parameters at time t. We choose a distribution q to tighten the bound. So it turned out here that q sub I of zi becomes the true posterior. And this is sort of how we formulated things for Gaussian mixtures. And then for a fixed distribution q, we can choose theta to maximize the bound, which will lead to familiar closed form updates. So this is a somewhat more advanced way of describing what we just learned step by step for the Gaussian mixture model. It's basically saying the same thing. Possibly later on in this course, or possibly in a subsequent course, you can return to this slide, and what I just mentioned will make a lot of sense, but I wanted to put a flag in it because this sort of step-by-step specific construction of how we do expectation maximization with mixtures of Gaussians, specifically with mu's and sigmas and omegas, generalizes to other forms where we have other distributions of probability called Q. And then how we conceptualize that as sort of these tightening and maximizing these bounds, which again might not sound too familiar to you, and that's totally fine. Okay, you can feel free to skip over this for now. The overall result of this theory, though, is that expectation maximization guarantees that the log likelihood will not decrease every iteration. Okay, but it can get stuck in a local maximum. So if you were to run a code doing expectation maximization, the log likelihood of your parameters and data together will keep getting better and better and better, and they'll never get worse, at least if you've structured things cleanly. There are kind of specific versions out there which are well advanced from our current perspective, where things could get worse, but we're not nearly there yet. So in most cases, and the one we just recognized, this Gaussian mixture modeling, if you're doing a mixture of Gaussians, and you're modeling them, then your models will always get better and better and better as you go through more and more iterations. The problem is, like we talked about earlier, the kind of loss surface that we're trying to climb in order to find parameters that give us the highest probability or the likelihood. There's many peaks and many valleys. So as you're kind of climbing the surface, you could get stuck in a place where you can't seem to get any better, but there could be just over the next horizon another peak that's even higher, an even better representation of the data. Because machine learning is so closely related to statistics and to some extent mechanics, there's, again, I think we already made reference to this McKay reference here, but you can go ahead and get this as well, specifically chapter 33. So, taking a step back, we kind of assumed that we're observing data points, and we're assuming that kind of conceptually that these data points are being observed either from one mode or the other. That could be true in some situations. It could also not be true in some situations. We don't really care at this point. That's just how we're conceiving of this hidden state. Okay, so we don't actually observe this black like multimodal distribution that we imagine exists. All we see is the individual data points X as they're being generated. But we're imagining it looks sort of like this. Okay, so it's going kind of fast, but all of these data points that I'm generating are generated either by component 1, this blue component, or by component 2, this orange component. Okay, so in reality, that's what's happening. I imagine, right? So blue's generating data, X is generating data, and when I learn a distribution to try to fit all of these observations, that will get me something closer to reality, which is this black curve. Again, which I'm imagining. I'm making all of these assumptions here. But this is generally how we're imagining the data generation process to look. All of my data points come out either from blue or from orange, and what we have is, given a data point, kind of to guess whether this came from blue or from orange. Here's another little visual, which kind of tells us what that probability is. Okay, so I'm going to scan this red line over different possible values of X, and on the right over here, you're going to see the posterior probability of hidden variable Z, which is component 1 or component 2, given the particular value of X at that time. Way over here, this is kind of, this is very, very simplistic, okay? So this is purely for the purposes of illustration. Way over here, I'm much closer to the blue component, so I can say, well, the probability that the blue component generated it is infinitely higher than the orange component. There's a 100% probability that the blue curve generated something way out here at x equals minus 4. As we look at variables closer to x equals 2, the orange curve will begin to rise imperceptibly for a very long time. And it's going to remain a very high probability that component 1 generated an observation at value x. But as I continue to look at bigger and bigger values of x, at some point it'll be very uncertain to me whether or not component 1 or component 2 generated this particular data point. You'll see when. It should be obvious to you where that is. And as I keep on going to the right to bigger and bigger values of x, the kind of the responsibility to generating these data points, at least in my imagination here, is more or less going to be assigned to component 2 to a greater extent. So hopefully that makes sense. Let's see what happens. As we get to bigger and bigger values of x, the probability of the responsibility for generating that value x shifts from almost certainly coming from component 1 to being very uncertain between them to having a very high probability that component 2 generated that observation. We can also visualize what I just kind of animated a moment ago. Here's again my values of x, which going back to the turbines is our vibration amplitude. Here's the responsibility for component 2 specifically. Because I only have 2 components, you can kind of see the inverse of this. So the probability that component 1 generated this particular value of x is just sort of the inverse, or the remnant of probability. So here I have 100% probability, or nearly so, for x equals 5 that component 2 generated it, which translates to a 0% probability that component 1 generated it. However, like every data point, even the ones in the extremes, belong, speaking loosely, to every cluster at least a little bit. It's not just the ones in the middle here where I'm quite uncertain that, well, component 1 or component 2 could have generated this. I want to kind of allow for the fact that even in the extreme cases, either component could technically have generated this observation. So EM, in practice, has a ton of strengths. It handles missing data, a hidden structure, naturally, has these latent variables, which we've defined. And we've gone through the example of Gaussian mixture models. I hinted at the fact that we don't have to use Gaussian mixture models. We can use other probability distributions, other structures, and expectation maximization, the core idea, will still work. We still infer the hidden structure. We use that inference to then do maximum likelihood estimation, and we iterate back and forth. The ML step will look very familiar to MLE updates. So we want to do MLE. We kind of can't, but we can kind of estimate it kind of in a soft fashion using the weights we computed previously. And it's going to look different for different distributions. Like I mentioned earlier, there's a monotonic increase in log likelihood. Every iteration, you're getting better and better representations of your parameters and the training data. So it's not a random walk. It's directed and it's purposeful, which is great. And it's used widely. So mixture models like the ones we talked about, clustering, density estimation, so basic data science. Hidden Markov models is something we might touch on later in this course. It's not as popular as it might have been, 5 or 7 years ago. But even today, there are deep neural network models that use some variant of hidden Markov models within their complicated construction. And HMMs use expectation maximization in computing their hidden variables. The H in hidden Markov models explicitly stands for hidden. So time series, like speech, is a time series. Some variants of topic modeling in text, factor analyzers will use expectation maximization. And then I've linked to a bunch of other papers here on deep learning. You can find these at the reference section at the end of the slide deck. But as you can see, a lot of these deep learning papers are, still pretty recent and being published in competitive journals like NeurIPS, conferences like NeurIPS. So even though expectation maximization is brilliant, there are pitfalls. Like we talked about, the objective is non-convex, so EM can get stuck in local maxima. The results can depend heavily on initialization. So again, imagine a mountain range, which is your loss surface, and we're trying to climb a mountain, right? If you started at the base of Mount Everest, you're going to climb that mountain and you're going to end up with a global maximum. But if you started off at the base of Citadel Hill in Halifax and you climb that hill to the very beautiful looking fort, that won't be nearly as high as Mount Everest, right? So where you happen to start has a huge effect on where you'll end up using expectation maximization. Label switching. So the problem here is that, I called component 1 and component 2, but I could have switched those labels. This is what I kind of mentioned right off the bat. Like when I talked about the turbines, I assumed that, we have a normal mode and a failure mode or a risk mode. And I assumed that I knew what those two things were, but I don't. All I have is a variable Z. Z could take K components. K can be 1, 2, 3, 4, 5, whatever. But what the particular value of K means is not known to us at this point, right? All these labels are interchangeable, meaning that I can't specifically say, well, this component which does this is responsible for my observation because I don't know what this is. It can produce degenerate solutions. So Gaussian components can collapse into single points where you have zero variance. This is a kind of side case which we're not going to get into much now, but it is possible that some of these components in these Gaussian mixtures can just combine, can just collapse. Sigma squared gets, the variance goes to zero or close to zero, and then the Gaussian kind of disappears, which is not great, and that can degenerate the overall solution. You have to choose the number of components k, right? So before I kind of went over this, like you have a big K, which is the number of components, and it's known, and we'll just run with that. But, I didn't mention that you have to choose that. So is the best value 2, or is it 2,000? Right now, we have no inclination for what the optimum value of K should be. Of course, there is an optimum value of K for our data set, but we'll talk about how to find those things later in some other module. There are also a lot of assumptions. So I assume that there's something there. I assume that there's one variable z. Maybe there's two hidden variables that compete with one another, right? And what are the actual facts, the theory behind the scenes? There's a lot of shortcuts being taken with the interpretation we have here. Okay, so interpreting these clusters, so learning a model that might have a very high log likelihood for the data might lead us to want to interpret these clusters as there's definitely one cluster here called component 1, there's definitely another cluster there called component 2, but that's not necessarily true. That's a convenience that allowed us to obtain a tight probability distribution, but we can't describe any meaning, again, to those components. I think I'm kind of repeating myself, but I think with good reason. We want to build complex models, and this helps us to do that. So let's go all the way back to our original decision, returning to the vibration monitoring scenario. Expectation maximization, using Gaussian mixture model will, for each time window, each like observation, give us responsibilities for that time window I, that one of our hidden states K produced this observation. And this is where we kind of really lay on the assumptions thick. We can imagine we know that there's the value of z sub I equals high where. We have a label now. And again, like I mentioned a moment ago, this is not going to be the case. I can't emphasize this enough. But when you do expectation maximization, the hidden states kind of usually by default mean nothing. And now I'm ignoring that and saying, well, z sub I actually means high where. And I'm computing the responsibility gamma sub I k, where this is telling me the responsibility of k is high where. This is a turbine we need to check out. Okay, but I can kind of turn this into a decision rule. So if I had that, then I could turn this into a decision rule. If I learned my model and then I observe a particular observation of a turbine's amplitude or vibration at iteration I or time I, what is the probability that I'm in a high where or risky state? I can compute this probability using the methods I mentioned earlier. I can compare this to some threshold, which I have to define, 0.8 for example, maybe 0.9, maybe 0.7. This is up to you. And if this condition is met, then I can flag that turbine for inspection. Otherwise, just let it run until the probability of being high wearing, given the observation, is above this threshold. Okay, so fine, but if you want to do decisions well, you're still going to have to rely on model checking. So do the residuals or misfits suggest the GMM is wrong, or outliers? Like what do outliers have to say about our Gaussian mixture model? How often would we miss actual failures versus over-inspect? The original kind of risks, the costs we had with false positives and false negatives come into play now that we're starting to make decisions. And how those costs are computed, well, you have these contexts. So what is the cost of downtime or a ruined blade versus the costs of actually going and inspecting things? So we're back to the original issue of stakeholders making decisions based on probabilities that we computed, and we computed probabilities in this case using Gaussian mixture models. So this looks a lot like classification, like we mentioned earlier. So if we're trying to compute the probability of label high risk or a high where, given some observation, this looks a lot like classification. And to be honest, sometimes it is used as classification. So hidden Markov models, for example, will guess at hidden states, but then the hidden states will combined be used to say, well, this is, word whatever in speech recognition. It's a bit, we'll come back to that possibly later. Anyway, the idea is that expectation maximization produces soft labels. It doesn't produce necessarily an actual like single decision, but as we saw earlier, we can still do classification based on these soft labels. So we saw like logistic regression. Logistic regression, the labels are given during training. So we have an actual mapping from X to Y that we're trying to learn. This mapping is probabilistic, but given these probabilities of Y, we can still use those to do classification to predict the correct label. We know the correct label if it's given to us in supervised learning, and expectation maximization is not supervised learning. I want to reemphasize that. It's purely unsupervised. Latent variable modeling, so Gaussian mixture models in our case, being trained using the expectation maximization algorithm. The labels are never observed, despite what I mentioned a moment ago, just to kind of bring things into focus a little bit. Our goal is to guess at the hidden structure. Once we have the hidden structure, maybe we can use the parameters of that hidden structure to say something about the data. We won't always be so lucky as this contrived case over here, but it's possible. And along those lines, if you can somehow, with confidence, using some other information, say that component 1 is definitely high wear and component 2 is definitely normal operation, then you've converted this unsupervised training of Gaussian mixture models into a classification task, which we thought was kind of impossible previously. Might have thought anyway. Our one sentence takeaway is that classification predicts labels that we already have. Expectation maximization discovers structure that you don't directly observe. So in our example, we talked as if we already had that. This was a shortcut. I think I mentioned all of this already. In real deployments, you don't know how many regimes or states or hidden classes or components exist. We had to guess at what the value of k was. We don't know what they mean ahead of time. Again, all we have is the observations x. We do not have any hidden state, right? So there's lots of assumptions behind the scenes. But we do have a principled way of discovering some hidden structure if it exists. Maybe doing some follow-up discussion on that afterwards. And later words should be a word. I think it is now, so I'm happy with that. This is also good for uncertainty-aware assignments. So throughout this course, we'll talk a lot about sort of Bayesian models and describing uncertainty and entropy and those kinds of terms. So thinking probabilistically is helpful. So not saying necessarily, I know that this observation came from this labeled component, but having a soft combination of various different possibilities is in my mind a much better way of envisioning the universe and our data. And this is a density model, so we can kind of like say, we can describe how likely it is that our data is coming from one of these modes that we've learned. And if we see some data which is far outside of these different peaks or modes we've learned, then we might be able to say something about anomalies or outliers, or detect that something's changed in the world. We're monitoring the deployment of a model, and therefore that we need to maybe retrain things. So again, I just caution you against treating this as a classification. So sometimes you can discover regimes, but because there's no modes, you can't always. If you're doing clustering, and you don't really want to do classification, then you're not doing classification. Density estimation, anomaly detection, this example I just mentioned, are not really classification tasks. They're more like clustering tasks, unsupervised learning, classic unsupervised learning tasks. If you have missing or partially observed data that you need to kind of synthesize, especially in the case of generative modeling, then you're not, generative modeling can sometimes be described as a form of classification if you're generating actual text, say, but in practice, this is all probabilistic, and considering it to be strictly classification might be the wrong way of thinking about a generative model, right? When you're talking to ChatGPT, for example, and is writing all the text on the screen, or Gemini, or Claude, or Llama, you see one word appearing, but there's other words behind the scenes that could have been written at that particular point, and we just happen to observe this particular observation, which brings us back to the physics example. But again, we're not physicists, so we don't need to talk about that at the moment. So logistic regression, like our previously best way to do sort of soft classification, can't even be written down for these kinds of tasks. So we wouldn't frame these tasks as classification generally. So I want you to remember everything, but if you only remember 3 things, I want you to remember the idea of latent variables. These are hidden labels or states, something behind the scenes that we never actually see directly, but we can guess or assume are there. We have to assume something about the structure. We may have to assume how many possible labels or states exist. And if we can guess at that, then suddenly we can do maximum likelihood estimation, which we previously saw to be very, very effective and fast and advantageous in other theoretical ways. How we can do that is through expectation maximization. So we can guess at the hidden stuff, the hidden latent variables. That's the E step. Given our best guess as to what's going on behind the scenes, we can use that to refit the parameters, which is the M step, which is essentially MLE. And then we repeat the E step and the M step back and forth until we have some kind of stopping condition. We can turn this into a classification tool if we're very careful. The vibration example was one such example, but I just, again, caution you against conceiving things in those terms, because the hidden state was something that was entirely made up by us, and certainly the labels were. So yeah, classification, this is a fourth thing. Surprise and fear, fear and surprise, and the fourth thing is classification predicts labels you already have. EM discovers structure you don't observe. I guess this is really, a recasting of what I just mentioned a moment ago, but that's an important thing to remember. I love expectation maximization, and we're going to see a little bit more of it throughout the class, in some code for it, and you're going to play around with it. So we've established the idea of latent variable models. We've established the idea of the EM algorithm, how it connects to maximum likelihood, and we've seen one possible way that we can implement EM, specifically in Gaussian mixture models. And like I mentioned before, there's other kinds of models we can have in which EM could apply. It would just learn different parameters. It wouldn't learn Gaussian means and Gaussian variances. It would learn something else, but the overall iteration of E and M steps would still apply. So later, we're going to apply EM style thinking to other models. We're going to connect more general variational inference ideas to this, and we're going to continue to tie our learning objectives to some real decision problems as much as possible. We had a fair amount of references today, so please read all of them, and I'm looking forward to seeing you next time.